So. Все записались. Была информация, что кто-то не из вышки хотел посещать курс. То есть там вроде есть какие-то данные, кто записался, но я думаю, что лучше все-таки по факту, кто ходит, понять. Okay, so we should start. Yeah, so okay, so I suggest to complete the missing parts in the description of a complex structure on the torus. So what we left for seminar, that the map is open. Yeah. So okay, maybe. Okay, so what is left? The first, that the map pi is open from C to C over gamma. Is open. And second, that then all complex charts of this form, of the form that we considered, are compatible. All the complex charts that we constructed are compatible. Okay, so who wants to do something from this? Okay, so how to do that? So one of the part of the final grade is work on the seminar, so it will be recorded who worked on the seminar.
Well, let V be an open substantive in C. What we need to check is that inverse of pi of V is open. Because this is how we define open sets in the quotient. Well, this is just, I believe it is just V plus gamma, because it is all of the elements that are equivalent to, an element lies in here if it is equivalent to any element in V. I believe it is so. So this is the set, and it is obviously open because it is a union of many open sets. So it's trivial.
Yeah. Yeah, I mean, yeah, actually probably this notation is fine, but I guess people don't. I mean, I guess you consider, of course, the union of pairwise sums, but I'm not sure that people often write like this. Okay, I think it's better to write union omega plus V. Yeah. Yeah, okay, this is the same, but I just say that, I mean, I think people don't write like this. Okay. Yeah, indeed. Yeah, so this is union of open subsets, so it is open. Yeah. Yeah, okay, this is fine. Okay, so what is your name? Как вас зовут? Как? Спирин Степан. Ага, хорошо. Ну хорошо. Хотя, наверное, им фамилия достаточно. Okay. Who wants to do the second one? Probably it's a bit more, yeah, maybe it's less easy. So what? Yeah, by the way, are there any questions about the first one? Okay, I guess it was not hard. Okay, just I mean, just to write what we want to prove. Yeah, so we have V1, V2 in C. Yes. Yeah, then okay, I mean, we have, of course, this condition that Vi intersect at omega plus Vi empty for yes. Yeah, so we have V1 pi yeah, so what we have the intersection V1 V2 no have pi of V1 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 and then the inverse is phi 1 and then this phi 2. Yeah. Okay, yeah, and then okay, I just okay, probably yeah, I just write what we want, yeah, so phi 1 phi 2 phi 2 yes. Yeah, and then we want to check that this map is biholomorphic. Phi 1 phi 2. Yeah. So so yeah, this is biholomorphic. 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 So there is one English, at least one English-speaking person. Can you speak in English?
А я вообще без слов, наверное, могу.
Ну ладно, тогда уж словами. Мгм. Ну, ну как бы это элемент же в этом, ну, в C, в Торе, в C по гамму, да, ну очевидно, это же 0 просто, ну просто 0 добавили, да?
Сейчас. Вот так.
X в пересечении, да.
Потому что
Мгм. Ну да, потому что да. Не, а почему оно непрерывно? Почему вот это непрерывно? Why Vx is continuous? А,
непрерывно, потому что
не, ну конечно, это же разность, извините, да, ну конечно, это же разность непрерывных функций, да. Да, то есть, ну, φ2, текст, φ2 и φ1 это же непрерывные функции, ну их разность тоже непрерывна.
вот, ну, непрерывное отображение в дискретное пространство постоянно.
Да,
То есть вот эта функция — это прибавление константы. Значит,
да. Ну, на связанной компоненте. То есть, получается, да, Vx принадлежит гамма, Vx is in gamma, Vx is a continuous function, as a difference of continuous functions. So Vx is constant on connected components of U1 intersected with U2. Yeah, so um,
ну и нужно, значит, нужно понять связанность.
да,
Пересечение, а не все пересечение.
да, да. Okay, so yeah, so it's yeah, it's correct. I just just write. Probably we have to write somewhere else. Yeah, so Vx is continuous as a difference of continuous functions, and so it's a map to a discrete set. So, okay, so Vx is constant on the reducible components on the connected components components of yes, but then here I don't understand what you write, yeah, because what does it mean? I mean, this is a function. This becomes a function on an open subset of C. Yeah. So X. I mean, what does it mean? So X is a point in the torus. Hmm. Hmm. Yes. Okay. Yeah. Yes. Yeah. So yeah. So then it means that this thing, yes, on the image of the connected components of X is equal to Vx. Yeah. So I mean, as a constant function, it is biholomorphic. Yeah. So, are there any questions about this proof? Yeah. So basically, yeah, he proved that this map. Yeah. Basically, here he proved that this map. Yeah. Phi to composition phi 1 inverse is locally constant. So it is biholomorphic. Yeah. Okay, so if there are no questions, then we continue. Okay, then let us consider these complex tori in more details. А как вас зовут, чтобы я записал, отметил ваш... Как? Илинский. А имя? Как? Да. Okay. Okay. So yeah, okay, probably an obvious remark. So remark. That okay, again we consider the complex torus corresponding to the lattice then of course yeah, so omega 1 and omega 2 is a basis in this lattice, but of course we can choose another basis here, but yeah, we can choose another basis, and then the transition matrix is given. A transition matrix between different bases are given by matrices from SL to Z. Yeah? So if A is some matrix in SL to Z, then yeah, so this by this I denote the set of 2 by 2 matrices with entries from Z and with determinant 1. Then for omega 1 prime, omega 2 prime in C defined by one prime A omega 1 omega 2 we have that yeah, the lattice generated by these two numbers is the same as gamma. Yeah, so gamma prime Z is equal to gamma. Okay. I mean, this is an obvious remark. Okay, then another exercise. Another exercise. Okay, prove that if two lattices are okay, so prove that C over gamma okay, yes, it was not good that I did not have time to introduce the maps between Riemann surfaces. Okay, and this is simple, so probably I give a definition. Yeah, okay. So if so definition. So if x, y are Riemann surfaces, then a map F from X to Y is called holomorphic. If for any complex charts, for any charts phi 1 u1 to v1 on X and phi 2 u2 on Y, on V, no, on Y, such that is a continuous map. Let us say a continuous map. Continuous map such that f of u1 is inside u2. We have I mean the map what we want phi 1 of I mean from v1 to v2 to v2. And what is this map? We take phi 1 inverse, composition F, and phi 2 is holomorphic. is holomorphic. Holomorphic. Yeah, so yeah, standard thing. So we have u1 in x, u2 in y, and we have these v2, phi 2, f. And then we require that this map should be holomorphic. See. Okay. Yes, and as usual, it is enough to check it locally. Yeah? Again, the same remark. Probably I just say it in words. So enough to check it. Enough to check it locally around any points, any point of x. To check it locally around all points p in x. Yeah, meaning that it's enough to so for any point p in x, it's enough to find an open chart containing p and an open chart in y containing the image, such that f of u1 is in u2 and this condition is satisfied. Yes. Okay. Yeah, I guess it's clear what I mean here. And then, yeah, and then okay, there is of course there is notion of isomorphic Riemann surfaces. Just yeah. Yeah, so and then, of course, an obvious definition. So x and y are called isomorphic. If there is a homeomorphism f from x to y such that f and f inverse are holomorphic. Okay. We have this definition. Yeah, and then okay, then I can. Are there any questions about this? Okay. Okay, and then the exercise was to prove that C over gamma is isomorphic to C over the lattice A times gamma for any non-zero complex number, yeah? A in C star. Yeah, so A gamma is just what? We just Z A omega 1 plus Z A omega 2. Yeah. So if we multiply a lattice by any non-zero complex number, we get an isomorphic Riemann surface. Yeah, I mean, I guess it's yeah, it may be obvious, but yeah, the idea is to yeah, explain it rigorously from the definitions. Yeah, so first we should construct some homeomorphism.
The isomorphism is induced by identical map of not factorized complex plane.
Um, so you want to take some map between complex plane, between from C to C, yeah? What map? Just the identity? But then how does it induce a map from one torus to another one?
Классы одинаковые.
То есть вы хотите построить отображение, да? То есть, ну, let us construct, yes, okay, proof. Let us construct a map, a map from C to. So how do you want to construct it? Okay, so we take some point in C gamma, and then
Класс X переходит в класс X. То есть X переходит в класс любого представителя X, потому что это то же самое множество.
то есть, okay. So okay, so take okay, let us construct a map, yeah, F. Then what you say take a representative.
А вот X это орбита любой своей точки при действии SL2Z.
Uh,
SL2Z переводится в себя полностью при применении
Ah, yeah. Okay, I mean, okay, I just want to write what you suggest. Yeah, so you take a representative x tilde of x. Yes. And then, I mean, of x, I mean, mod gamma. And then you want to define as f of x the representative of x mod a gamma. Ну, короче, как вы определяете? То есть вы хотите, вы говорите дальше, определим.
Я сначала утверждаю, что класс эквивалентности слева это точность класса эквивалентности справа. Потому что каждый класс там и там является орбитой какого-то вектора при действии SL2Z.
Ну, А-то, она из C со звездочкой. Правильно. Ну, вот у вас есть представитель X, да? Но разные представители отличаются на решетку гамма, да? Но решетка гамма, она же не совпадает с решеткой А гамма.
Они, в частности, отличаются от применения SL2Z в базисе решетки гамма, а SL2Z в базисе решетки гамма это то же самое, что SL2Z в базисе решетки А гамма, потому что SL2Z в базисе решетки А гамма это SL2Z в базисе решетки гамма умноженное на А. А умножение на А это оно сюрреактивно, это сюрреактивное окружение за SL2Z в себя.
Я это понимаю, но как вы отображение строите? То есть,
Я доказал, что классы слева и класс справа это одно и то же, я просто перевожу в поле.
да. Ну, понимаете, да? То есть теперь хорошо, окей. So, вы говорите, что take as f of x in C over A gamma. То есть класс эквивалентности x относительно гамма. Так что ли вы хотите? The equivalence class of x mod the lattice A gamma. А почему вы говорите в SL2Z? У нас SL2Z, A все-таки это комплексное число. So it is not, I mean, this is not correctly defined, yes, because да-да, вот я вот несколько раз поэтому говорил, что это комплексное число. Может, если вас немножко смущает, то альфа, не знаю, там, греческую. Изозоморфик, то yes, альфа. Map. Take the equivalence class of so, but I mean, this is not correctly defined because if you choose another representative, if you have for another representative, I don't know, x prime of x, so the equivalence, the representative x tilde, sorry, f of x, the equivalence class of x tilde. It's a representative. If you have another representative, I don't know, x tilde hat, x hat of x, meaning that x hat minus x tilde is in gamma. I mean x hat minus x are not equivalent, are not necessarily equivalent mod alpha gamma. Yes? I mean, sorry, it's not necessarily in alpha gamma. Yeah. Ну да, то есть надо на альфа умножать, да. Ну да, то есть действительно, то есть да, отображение строится просто умножением на альфа, да, то есть как оно строится. Окей. So what is the correct definition? Let us construct a map from this torus to this torus. Okay, you take some point in the first torus and take a representative x tilde of x mod gamma. Yes, and then take fx as f of x in this torus. The equivalence class of alpha x x tilde mod alpha gamma. Yeah. So, and then clearly, I mean, this is f is well defined. F is well defined. Indeed, if x is another representative of x mod gamma, then, so what it means? It means that x hat minus x tilde is in gamma. But then, of course, I mean alpha, then alpha x hat minus alpha x tilde belongs to alpha gamma. So alpha x hat minus alpha alpha x hat is equivalent to alpha x tilde mod alpha gamma. Yes, and okay. Okay, and then I mean it's a standard exercise in topology that f is continuous. Yeah, so f is continuous yeah, and of course I mean the inverse is given by the division by alpha, so f inverse is also continuous. Yeah, f inverse is given by the multiplication by alpha inverse. Yeah, so it is also continuous. Okay, so we have a homeomorphism, and then one has to check that it's biholomorphic. So one has to check that f is biholomorphic. Okay, so how to check it? Huh? Yes, yes. So we what we do? Yeah, so we take how to do it formally. So we take a complex chart complex chart phi is u v that we can on C that we constructed of the form that we constructed of the form that we constructed that we considered. Yes, yes, and then, yeah, then okay. I mean, it's then we take, and then we take take as v tilde just alpha v in C. Yes. Okay, maybe So maybe okay. So just to have notation, so we have a canonical projection from C to C mod gamma, and then we have let us denote it by p tilde the canonical projection from C over alpha gamma. Sorry, from C to C alpha gamma. Yeah. Then we take as v tilde alpha v and u tilde as pi tilde. Okay, yeah, I mean this. I just want to construct a complex chart on this torus, just by multiplication of this chart by alpha. Yeah, pi tilde of v tilde. Yes, and then f maps u to u tilde. Okay, and then this map. So we have u tilde. We have here phi to v tilde. This f. And this map. I mean this map just is given by multiplication by alpha, yeah, and then phi inverse composition f composition phi tilde from v to v tilde is just multiplication by alpha. Is the multiplication by alpha. Yes. Okay. So so for any complex chart in this torus, we constructed a complex chart on the second torus, yes, such that okay, actually this is homeomorphism. But okay, it's important that f of u belongs to u tilde, and then yeah, this map is just multiplication by alpha. Okay, so it is holomorphic. So f is holomorphic. Okay, and then the inverse is given by the multiplication by alpha inverse, so is also holomorphic. Okay, so are there any questions? Yes. Good. Then it was some technical thing for what? Yeah. So the second exercise is then now prove. Okay, what is the fourth, fifth? Probably the fifth. Prove that any complex torus C is isomorphic to a complex torus of the form torus complex torus of the form C mod, and here we write z plus z tau, where tau is a complex number with the property that the image of tau is greater than 0. Yeah. So yeah, so we considered complex tori where the lattice can be generated by arbitrary two complex numbers that are linearly independent over R. But yeah, this exercise says that all such tori are isomorphic to tori of the form where 1 omega 1 is just 1 and omega 2 is tau. Yeah, image of tau greater than 0. So yeah, so we can yeah. So any complex torus is isomorphic to a special complex torus where this lattice has this form, special form. Generated by where the first vector is the unit and the second vector is an arbitrary number with the image imaginary part greater than 0. Ну да, да, это выводится, да, и как же выводится? Поворачиваем. Хорошо. Okay, so we consider arbitrary proof. Okay, so you consider arbitrary torus, yeah. Well, then what you do? What you say? Okay, what does it mean? How to? Okay, maybe you can come and and write something.
Multiplication by complex number is nothing but rotation
Mm-hmm.
and gmatation.
Uh-huh.
So we can first of all we can rotate this pitch by multiplying by something like this.
Mm-hmm. Mm-hmm.
Now you can just take
Mm-hmm.
1 over r and so this is
Mm-hmm.
unit vector. This is
Mm-hmm.
tau.
But maybe tau, you have another option that maybe it's the imaginary part is negative.
But if we get like this, then we can again rotate and rescale. So here we actually choose these vectors to be counterclockwise.
Mm-hmm. Yes.
You always can do this.
Yeah. Yeah. Okay. Yes. I mean, yes. Strictly speaking, what you say that consider omega 1 and omega 2 and consider this angle. Yes.
Yeah,
This
yes, okay.
angle alpha. So if alpha is greater than pi, yeah,
Mm-hmm.
then you just then that just switch. Then switch.
Yeah, so actually this means that imaginary part of omega 2 divided by
Да.
omega 1 is
Yeah.
less than 0.
Yeah. Yeah, I mean, of course, it's correct. Yeah, just okay. One way to say that if alpha is greater than p, then just switch omega 1. this pair replaced by omega 2, omega 1. Yeah, because this doesn't change the lattice, of course, so you can switch.
Okay.
So if you have this picture, so picture like this, right, okay, the picture like this, so meaning that this is greater than pi, then you just call call the second vector omega 1 and the first one omega 2. Yeah, and then this angle becomes less than pi. Yeah. So yeah, so without loss of generality, we can assume that alpha is less than pi. Yes. Okay. And then your argument. Yes. So indeed, then yeah, you can rotate and make the first vector just a real number, positive real number. Yeah, and then divide by r. Yeah, and but I mean, in order to get complex torus, they should be linearly independent over R. Yeah, so they can't be simultaneously real. Yeah. So in particular, I say that alpha is greater than p. So, but alpha is not equal to p because because omega 1, omega 2 are linearly independent over R. Independent over R. Yes. Okay. Yes. Yeah. Как вас зовут, чтобы записать? Мартынюк. Да, хорошо. Okay. Are there any questions? Okay. If there are no questions, then okay. And then the goal. What is the final exercise about this torus? Is that actually there's a further reduction. There's a further reduction. It says that actually this tau can be chosen to be in some particular region. It's probably the sixth exercise. The sixth exercise. Prove that any complex torus. Now, okay, we know that we can make it of this form. Z plus z tau is isomorphic to a complex torus of the form plus z tau, where yeah, again, the imaginary z tau tilde, where the imaginary part of tau tilde is greater than 0. The absolute value of tau tilde is greater or equal to 1, and the absolute value of the real part of tau tilde is less or equal than 1/2. So this can be further reduced. This tau, and this is this picture that you see that tau, I mean these inequalities mean that tau belong to the following region that you probably saw this picture before. So okay, minus 1, 1. Here we have minus 1/2, 1/2, and then you have this yeah. So Yeah, so yeah, the statement says that we can choose tau from this region. But okay, maybe probably it's immediately it's too hard. Yeah, probably. Okay, this is really what we want, but maybe it will be the sixth, the seventh, but the sixth prove that C over Z plus Z tau is isomorphic to C over Z plus Z tau tilde, where where tau, I mean again, imaginary part of tau, where tau tilde is equal to A tau plus B over C tau plus C tau plus D. Where all these numbers are real numbers, and AD minus BC is equal to 1. Tau tilde.
Но это элемент S2Z, он объективно действует на решетку.
Да. Yes, indeed. Ну, хорошо, ну какое доказательство все-таки? Ну, слова-то понятные.
Факторизация слева справа по одной и той же решетке.
Ну, не по одной и той же все-таки.
Одно и то же множество точек. У нас же факторизация, это по определению там разность между...
Ну такая решетка все-таки она не совпадает с такой решеткой, правильно же? Да? Не обязательно. Ну, потому что здесь вы можете взять, например, ну, что, например, там, b равно...
У нас с такой решеткой поделенной, значит, правая решетка это левая, поделенная на...
Ну да.
c тау плюс d.
Да. То есть proof indeed that we know that C over Z plus Z tau is isomorphic to you just indeed apply to you can I mean actually it's the same, it's equal, C you can apply this matrix A B C D to these vectors. I said that if we apply such a matrix to this vector, then we get vectors that generate the same lattice. And this will be probably A plus B tau. C plus D tau. Okay. Okay. Maybe A plus B tau. I don't know. Plus B tau. C plus D tau. Maybe this will be better. Yes. So and here, so what we get? We get A plus B tau. And here we get C plus D tau. Yes, and we get C over A plus Z, A plus B tau plus, Z, C plus D tau. Yes. Because I mean, because this lattice is the same. But then we say that this is isomorphic. We multiply by C plus d tau inverse. So multiply by so multiply this lattice gamma, multiply gamma by C plus d tau inverse. Yeah, and then we get that this is isomorphic to C over, and we get Z A plus B tau divided by C plus d tau plus Z. Yeah, as we wanted. Yeah, we can change the order. I mean, because this doesn't change the lattice. Yeah. Okay.
How did we get the first equation?
This one. But I already said that that at the very beginning that if we have V1 and V2, okay, then they give a lattice gamma. But then if V1 prime, V2 prime is equal to A V1 W1 W2 and A is in SL2Z, then they generate the same lattice. Then Z omega 1 prime plus Z is equal to gamma. Yeah. No, they're just the same. Yeah. So I mean, just changing the basis in the lattice. So, yeah. So this is just a this is just another basis. Another basis in gamma. Yeah. Since the determinant of A is 1, yeah, so I mean you can express omega 1 and omega 2 in terms of omega 1 prime and omega 2 prime. So the lattice is the same. So I mean, so this is the equality. Yeah, and then and here this is the isomorphism that we discussed. That this is given by the multiplication by C plus d tau inverse, which is non-zero, of course, because yeah, the imaginary part of tau is not 0. Yeah. Okay. So. Yes. Yeah, so the 6, I guess the 6 should be clear. Yeah. Oh, I mean, by this equality, yeah. So, I mean, given two complex numbers, and when I say lattice, I mean the lattice, how it is defined, just Z omega 1 plus Z omega 2. The subset of yes, yeah, the same set. Yeah, the same subset of C. Yes. Yeah, actually, probably, yeah, strictly speaking, it should be better to write in another way because, okay, maybe, I mean, of course, it's the same, yeah. Yes, so write Z tau, okay, I mean, of course, the same, so Z tau, and then we act on the vector A tau 1. And then actually it's correct to write, it's better, I will say why is that, I mean, of course probably you know, C tau B, it's correct to write like in the way. No, I mean it's better to like this. B C tau plus D. I mean, of course, I mean everything was correct, but I will say why I changed it. So yes, A tau plus B, C tau plus D, and then yeah. So here we should better write A tau plus B, C tau plus D. Yes, and then yes. Tau, yes, and then multiply by C tau plus D inverse. So we get A tau plus B, C tau plus D. Okay, I mean, of course, everything was correct, but the thing is that okay, this was I mean, this was correct, and this computation before, but the thing is that note that that this guy also had imaginary part greater than 0. Know that if imaginary part of tau, then the imaginary part of A tau plus B, C tau plus D is also greater than 0 if A, B, C, D is in SL2Z. Actually, if you can note that if you write in another way, then it will not be correct. So I mean, so we want to consider tori where the imaginary part of is greater than 0. So I mean, then the correct way to change is this one. Actually, do you know this fact? I mean, usually this is proved in some other courses. That, yeah, do you know it? That if, I mean, okay, this fact that if that SL2 acts in the upper half plane, yeah. Do you want to? Okay, if somebody wants to make this computation, then we can do that. Does anybody want to do this? Okay. Okay, then I assume that everybody knows it. I mean, I think it's a beautiful fact, simple one, but okay. I think everybody should do this computation. And that if the imaginary part is greater than 0, then the imaginary part of this fraction is also greater than 0 for any matrix in SL2Z. Okay. Okay. So and then okay, we have 5 minutes probably. Yeah, we will not be able to prove it, but okay, at least to start. So then the 7th one, yeah. So so basically, I mean, okay, basically, what is the task? Yeah, to prove that acting by SL2Z, one can move a complex number inside this region. Yeah. So basically, idea prove that acting by, so moving tau to A tau plus B over C tau plus D, AB, CD in SL2 Z, we can move tau to this region. We can move any tau imaginary part of tau greater than 0 to this region, to this one, to this region. Yeah. So yeah, for example, okay, I mean, I just maybe the simplest remark about this strip. Yes, so I mean, since so the matrix 1, 1, I don't know, B gives the transformation tau maps to C tau plus D. So tau plus B. Yeah, for any complex, for any integer. Yeah. So it means that we can move tau to this strip, this one. Yeah. Minus 1/2, 1/2. Yeah. Yeah, but then the question why we can move it further to the region outside of the disk. Yeah. So this strip is clear, but this one now is non-trivial. Think. Yeah. Okay. Yes. Okay, we have to just finish. So 50 minutes. Okay, probably I have one more hint, but okay. Actually, yeah. So I think we should finish it next time. So you can think about it and show a solution next time. So yes, we finish for today. Ну понятно, ну вы, конечно, правильно говорите, но надо все-таки как бы строго обосновать, что мы так сможем делать, да? То есть, ну, как бы